Good afternoon to all of you. Now we are going to study next unit, the buffer cache. The syllabus is buffer headers, structure of the buffer pool, different scenarios for retrieval of a buffer, reading and writing disk blocks, advantages and disadvantages of cache, and for these whole points or whole syllabus of unit 2 buffer cache. The recommended book is a design of Unix operating system by MJ Batch, and the course outcome will be after completion of this chapter, a student will be able to implement different scenarios for the retrieval of buffer. So, what about the title? The title of this chapter is the buffer cache. As we have discussed the architecture of Unix operating system in chapter first, in that we have used a buffer cache for the fastest access device or memory. Buffer is nothing but temporary memory, temporary memory storage, and cache is the fastest access. So, meaning of buffer cache is collection of buffers with the help of which we can access data fastly from secondary memory to main memory, that is from hardware level to kernel level according to the architecture. What is the central idea of this chapter? This chapter covers what is the buffer cache, how the buffers are identified, that is with the help of buffer header, the structure of the buffer pool, different methods, that is different scenarios of accessing, that is buffer scenarios for the retrieval of buffer, reading and writing disk blocks from hardware level to kernel level or from kernel level to hardware level, and it also explains the different advantages and disadvantages of the buffer cache. What is the importance of this chapter in your syllabus? So, as our Unix operating system is multi-programming, multi-processing, multi-user environment, kernel have to execute data within less amount of time. So, accessing data from the secondary memory, that is from hardware level to kernel level, without buffer cache takes much more times. So, the use of buffer cache is the data transfer from hardware level to kernel level with the buffer cache. It takes less time. So hence buffer cache plays a vital role, that is important role for accessing data in turn in increased system throughput, that means output and response through. These are the assignment questions of this chapter. There are different algorithms we are going to study. Then this is the syllabus of this chapter, that is buffer header, structure of the buffer pool, scenarios of the retrieval of the buffer, reading and writing disk blocks, advantages and disadvantages of buffer cache. So in introduction, the kernel maintains files on mass storage devices such as a disk, and it allows processes to store new information or to recall previously stored information. When a process wants to access data from a file, the kernel brings data into main memory where the process can examine it, alter it, and request that the data be saved in file system again. From the example, for example, the kernel reads the data from the first file into memory and then writes the data in second file in the memory. Kernel reads data from the first file into the memory and then writes the data into second file. So just as it must bring file data into memory, the kernel must also bring auxiliary data into memory to manipulate it. For example, the super block of a file contains our file system describes the free space available in file system. Among the other things, kernel reads that the super block into memory to access its data and writes it back to the file system when it wants to save its data. Similarly, the inode describes the layout of the file. Inode, that is index node, which describes the general layout of the file. The kernel reads the inode into memory when it wants to access data in a file and writes the inode back to the file system when it wants to update the file layout. It manipulates this auxiliary data without the explicit knowledge or request of running processes. So kernel could read and write directly to and from the disk for all the file system access, but system response time throughput would be poor, that is output would be poor because of slow disk transfer rate, that is it requires more time, and that's why there is include there is a buffer cache so that the time required for data transfer from one file to another file with through buffer cache it takes less time, that is output rate will be increased. So the kernel therefore attempt to minimize the frequency of disk by keeping pool of internal data buffers called as buffer cache, which contains data in recently used disk blocks. So what is a buffer header? During system initialization, the kernel allocates a space for a number of buffers, that is particular buffer it gives a number to particular number to that buffer configurable according to memory size and system performance constraints. Buffer consists of two parts, memory array and buffer header. So a memory array that contains a data from the disk and buffer header that identifies the buffer, that is buffer number, because there is one to one mapping of buffer headers the data arrays. The ensuing a text frequency refer both parts as a buffer and context should make clear which part is being discussed. The data in buffer corresponds data in logical disk block on a file system, and the kernel identifies the buffer contains by examining identifier leads in the buffer header. So buffer header in memory copy the disk block and the contents of disk block map to the buffer, but this mapping is temporary until kernel decides to map another disk block into that buffer. So the disk block can never map into more than one buffer. The disk block can never map into more than one buffer at a time. If two buffers were contain data for one disk block, the kernel would not know which buffer contains correct data and could write incorrect data back to the disk. For example, suppose a disk block maps into two buffers, buffer A and buffer B. If kernel writes data first into buffer A, then into buffer B, the disk block contains contents of buffer B. If all write operations completely fill buffer, however, if the kernel reverse orders, then it copies buffer to the disk. The disk block will contain incorrect data. So this is the structure of buffer header. See this figure carefully. This buffer header has a different parts such as a topmost part is device number, then a block number, then what is the status of that buffer, then there are five different pointers. First pointer is pointer to data area, then second pointer to next buffer on hash queue, third pointer to the previous buffer on hash queue, pointer 4 pointer to the next buffer on free list, and last pointer to previous buffer on free list. So there is a free list, then there is a queue. So two pointers on free list, that is next buffer and previous buffer on free list, last two. Then these middle two pointers for on hash queue for next buffer and previous buffer on hash queue, and this first pointer is pointer for a data area. So buffer header, this is the figure for buffer header. It contains 8 points. Out of them there are 5 pointers and remaining 3 is a device number, block number, and what is the status of this buffer. Then pointer first refers to data area, pointer seconds, that is pointer to next buffer on hash queue, pointer third pointer to previous buffer on hash queue, then next pointer is pointer to next buffer on free list, and last pointer to previous buffer on free list. So this buffer header contains a device number field and block number field that specify file system and block number on that data on disk are uniquely identify buffer. The device number is the logical file system, not a physical device or unit number. The buffer header also contains a pointer to data area for buffer whose size must be as least as big as size of disk block. The pointer data area for buffer whose size is as per requirement of disk block, and status field that summarizes the current status of the buffer, whether it is free or whether it is busy. So The status of the buffer is a combination of the following conditions. There are nearly about five different scenarios. That conditions means there are a different five different scenarios, and on these five different scenarios there are a total six algorithms. These five scenarios contains five algorithms, and combination of all these five scenarios one algorithm. So that there are total six algorithms on this buffer header. So first scenario is a buffer is currently locked. Here a term locked and busy will be interchangeably as will free and unlocked. Second, the buffer contains a valid data. First is buffer is currently locked. Second, buffer contains valid data. Third, kernel must write buffer contents to disk before reassigning buffer. This condition is called as delayed write. Kernel must write buffer contents to the disk before reassigning buffer, and this condition is known as delayed write. Fourth scenario, the kernel is currently reading or writing contents of buffer to disk. Kernel is currently reading or writing the contents of the buffer to disk. And fifth, a process is currently waiting for the buffer to become free. The buffer header also contains two sets of pointers. The buffer header contains also contains two sets of pointers used by buffer allocation algorithms to maintain the overall structure of the buffer pool. The buffer header also contains two sets of pointers used by buffer allocation algorithms to maintain the overall structure of the buffer pool. So what is the structure of buffer pool? The kernel maintains a free list of buffers. A kernel maintains a free list of buffers that preserves at least a recently used order. The kernel maintains a free list of buffers that preserves least recently used order. The free list is a doubly linked circular list of the buffer with a dummy buffer header that marks its beginning and end. Every buffer is put on free list. Every buffer is put on free list when system is booted. The kernel takes buffer from head of the free list. The kernel takes buffer from head of the free buffer from head of the free list when it wants to when it wants any buffer, but it can take buffer from middle of the free list. But it can take buffer from middle of the free list if it identifies particular buffer in buffer pool. If it identifies particular buffer in buffer pool, in both cases it removes the buffer from the free list. When kernel returns a buffer to a buffer pool, when kernel returns a buffer to a buffer pool, it usually attaches buffer to the tail of the free list. According to occasionally to the head of the buffer list for error case, but it never to the middle. As the kernel removes buffer from the free list, buffer with valid data moves closer head of the free list. Hence, buffer that closer the head of free list have not been used as recently as those that are the further from the head of the free list. See, this is the structure of the buffer pool. This is a doubly linked list buffer pool. This is the free list ahead. Then attached buffer 1, buffer 2, buffer up to buffer n. There are this is a backward pointer, whereas this is the forward pointer. Okay, this is the original structure of this buffer pool. Suppose a kernel selects buffer 1 from this free buffer list. So buffer 1 is selected, it removes from this list, and the list will become like this. This is the pre buffer header, then it is attached directly to the buffer 2 up to buffer n. Whenever kernel takes buffer 2, then there is free list is attached to the free list header attached to the buffer 3 to n, and so on. Whenever buffer 1, here buffer 1 is removed from this list, whenever buffer 1 becomes free or becomes unlocked, then it comes to the last, that is after buffer n, it to the buffer free list, to this buffer pool. So whenever buffer 1 comes free, whenever buffer 1 becomes free, that is unlocked, then it will be attached at the end of this buffer pool, that is after buffer n. Okay, see the diagram carefully. Then move forward. When kernel access the disk block, it searches for a buffer with appropriate device block number combination. Suppose kernel selects a buffer from these queue, from this list. Kernel searches buffer from the list. Suppose kernel wants to buffer number 2 from this list. If it is in that free list, then it will remove that from that list. Okay. So rather than it search entire buffer, it organize the buffer into separate queue hashed as a function of the device and block number. The kernel links buffer on hash queue into circular doubly linked list. Similar to the structure of a free list, the number of buffers on hash queue varies during a lifetime of the system. The kernel must use a hashing function that describes the buffer uniformly across the set of hash queue. The kernel must use hash function that dis- distributes the buffer uniformly. that distributes the buffer uniformly across the set of hash queues. Yet the hash function has the simple so that the performance does not suffer. System administrators configure the number of hash queues when generating operating system. See this figure of hash queue. This is a hash queue header. Block number 0 mod 4, block number 1 mod 4, block number 2 mod 4, block number 3 mod 4. Why it is taken as mod 4? Because there are total blocks are 4. If there are total blocks of 5, then mod 5. This is block number 0, block number 1, block number 2, block number 3. This is a hash queue. It is a circular hash queue. Okay. So this block 0 contains buffer number 28, 4, 64 and so on. Similarly, this is a second hash queue, that is block 1, contains 17, buffer number 17, buffer number 5, buffer number 97. Similarly, this is block 2, which is a circular queue. There is a buffer 98, buffer number 50, buffer number 10, and last, and this is block number 3, which is in circular queue, which contains buffer 3, buffer number 3, buffer number 35, and buffer number 99. This figure shows the buffer on hash queue and headers of buffer and hash queue are. This is the headers. These headers on hash queue are the left side of each queue, and there are a square marked such as a 28, 4, 64 represents the buffers or buffer number on hash queue, that is block number 0, block number 0 mod 4, and it is the dotted lines between these denoted buffers present in forward and backward pointers. This is buffer is forward and back have backward pointers for hash queue. See this figure carefully. Buffer hash queue. So each buffer always exists on hash queue, but there is no significance to its position on hash queue. As stated, no two buffers may simultaneously contain the contents of same disk block. Therefore, every disk block in the buffer pool exists one and only one hash queue, and only once on that hash queue. And therefore, however, a buffer may be on the free list as well if its status is free, because the buffer may be simultaneously on a hash queue and on the free list. The kernel has two ways to find it. It searches on hash queue if it is looking for a particular buffer, and it removes a buffer from the free list if it is looking for any free buffer. There are two ways for kernel searching a buffer, it searches the hash queue if it is looking for a particular buffer, and it removes the buffer from the free list if it is looking for any free buffer. First, it is looking for a particular buffer, it search on hash queue and removes that buffer. If it is searching for a particular buffer on hash queue, but it does not find on the free list, then it will take or it will search for another free buffer on same hash queue or same free list. Then what are the different scenarios for retrieval of a buffer? So as seen, high level kernel algorithm in file subsystem invoke the algorithm for managing the buffer cache. Invoke the algorithm for managing buffer cache. The high-level algorithms determines logical device number and block number that they wish to access when they attempt to retrieve a block. For example, a process wants to read data from file. A particular process want to read data from a file, the kernel determines which file system contains the file. Firstly, kernel check for the particular file which is stored or in which file system that particular file be present, and which block in the file system contains that data. When about to read the data from a particular disk or particular disk block, the kernel checks whether the block in the buffer pool, or if it is present, okay. If it is not there, then assigns it to free buffer. When about to write data to particular disk block, the kernel checks the disk in the buffer pool. If not, assigns the free buffer to that block. And the algorithms for reading and writing these blocks use algorithm get block to allocate buffer from the pool. So there are 5 different scenarios. First, kernel finds the block on hash queue and its buffer is free. If kernel wants a particular block on that hash queue, or if kernel wants finds a particular buffer and that buffer is free. This is the first scenario. Second, the kernel cannot find the buffer, cannot find the block on hash queue, so that it allocates a buffer from a free list. That is, the kernel cannot find the particular block on hash queue, so it allocates a buffer from the free list. Third, a kernel cannot find block on hash queue and it attempting to allocate buffer from the free list, as in scenario 2. Okay, finds buffer on the free list that has been marked. If it find a buffer but that buffer has been marked as a delayed write, so kernel must write delayed write buffer to the disk and allocate another buffer. Scenario 3 is the kernel cannot find a particular buffer on the free list. Okay, it search for the another buffer on free list, but that buffer is marked as a delayed write, that is assigned to someone, and so kernel must write delayed write buffer to the disk, and so it allocates another buffer. Then scenario 4, kernel cannot find the buffer block on hash queue, and the free list on buffer is empty. Kernel cannot find the buffer on hash queue or block on hash queue, and the free list of buffers also empty. And scenario 5th, the kernel finds block on hash queue, but its buffer is currently busy. The buffer finds block on hash queue, but its buffer is currently busy. There are different 5 scenarios. Scenario first, once again I will take scenario first, kernel finds block on hash queue and its buffer is free. Okay, this is simple first scenario. Second, kernel cannot find a block on hash queue, and so it allocates buffer from a free list. This is second scenario. Third, kernel cannot find block on hash queue. It attempts to allocate buffer from a free list as same scenario 2, but it finds a buffer on free list that has been marked as a delayed write. That is, it requires some time to free that buffer, and so kernel must wait, or kernel must write delayed write buffer to disk, and that so that it allocates next buffer or another buffer which is free. Okay, scenario 4, kernel cannot find block on hash queue. Kernel cannot find a buffer on hash queue, and the free buffer list also empty. And last scenario, kernel finds the block on hash queue, but its buffer is busy. There are so in this way there are total 5 scenarios, that is different 5 algorithms on these 5 scenarios, and combination of these 5 algorithms becomes one algorithm, that is your sixth algorithm. In your syllabus there are nearly about total 35 algorithms. So out of them there are 6 algorithms in this chapter. So we move towards first algorithm for buffer allocation, that is a gate block algorithm. This is the name of algorithm, gate block. The input of this algorithm is file system number, block number. Then output of these algorithm is locked buffer that can now be used for block. So next step is, first is while buffer is not found. This is the first condition, buffer is not found to the kernel. Then it will check if block in hash queue. If it is present, then then there is it will check buffer is busy or not. For buffer is busy, there is a scenario 5th. So if buffer is busy, then goes to the sleep mode. Kernel goes to the sleep mode. That is, event buffer becomes free and up till continue. So back to again while loop, and it will check buffer not found. Then it will assign the block on hash queue. Then it will check buffer is busy. If it is free, if it is free, then mark buffer as busy. See here, first, first kernel found buffer. If it is not found, it is true, then it will kernel will check or search for the block on hash queue. If it found block and hash queue, there is a no block, so it will assign to the buffer, and buffer is busy. If that condition is true, then kernel goes to the sleep mode and go to continue, that is back to the while loop. Again it goes to the while loop. Again buffer will not found. Then again if condition, block in hash queue which is present. Now this is a present, then mark buffer is busy, that is allocate that buffer to the kernel. So here a scenario first, and remove that buffer from the list and return to the buffer. Here is completion of if condition. So if buffer is not on hash queue, then buffer is not on hash queue, then else part. So it will check if there is no buffers on free list, that is scenario 4. If there is no block, no buffers, then kernel goes to the sleep mode for the buffer becomes free, and again go to while loop, that is continue. So again go to the while loop, buffer is not found, so block in hash queue it is not found, so it goes to the next part, that is if it is found block and hash queue, then mark as a buffer and remove buffer from the free list. So remove buffer from the free list, and then if it is not found, then buffer marked from for a delay write, that is a scenario 3, and asynchronous write buffer to the disk and continue, that is back to the again while loop. Again rotate this while loop, and after else part, here remove for scenario 2, remove buffer old hash queue and put buffer onto new hash queue and return buffer. This algorithm is a gate block algorithm, that is a buffer allocation algorithm which combines all 5 scenarios. Okay, if you have any doubt in this algorithm, please ask. Then we will see a different 5 algorithms, that is scenario first, scenario second, that is scenario first, second, third, fourth and fifth, that is 5 different algorithms as per scenarios. And this is the algorithm is a combination of these 5 scenarios, that is a gate block algorithm, that is a buffer allocation algorithm. See the algorithm carefully. we move to the scenario first. The scenario first is a kernel finds the block on its hash queue and its buffer is free. This is your first scenario. Kernel finds block on its hash queue and its buffer is free. So this is the structure of first uh, hash queue structure. So this figure for a searching block 4 on first hash queue. So there are 4 blocks and at last there is free buffer headers. This free buffer list, there are free buffers are this joined number 3, then number 5, number 4, number 28, number 97, number 10. So these last buffer is free buffer is 10. First free buffer is 3, then 5, then 4, then 28, then 97, and then 10. This is the free buffer list. Okay, which points free list header, and there are 4 different blocks on hash queue. Okay, and question is a kernel searches the block 4 or buffer number 4 on first hash queue which is free. Kernel finds block on its hash queue and the buffer is free. See here, in free list it will check first it will check on its hash queue whether that buffer is free or not. If it is free, then allocates to the kernel. If it is not free, then it will check the free list. Okay, so figure defects. This figure shows the first scenario where kernel searches for block 4 on hash queue marked as block number 4. That is, on this hash queue, kernel search block number 4. If it is find, then it allocates to the kernel. If it is not, then it search on free list. This line or these different arrows indicates that this is the free list of buffer. So whenever the kernel finds whenever the kernel finds the particular buffer, then it removes from that free list. See, see this figure A. Figure A contains free list as buffer 3, then 5, then 4, then 28. If kernel wants or kernel searches for particular buffer number 4, then it will be removed from that free list. That is from, see in figure B, there is a free list contains 3, 5, then 28. In figure A, after 3, 5, there is 4. In figure B, after 3, 5, 28. Then 97, 10. So kernel finds a particular buffer on hash queue and its buffer is free. Then it removes from that free list and allocates to the kernel. Okay, this is the first scenario. So for finding the buffer, kernel removes from the free list and leaving blocks 5 and 28 adjacent on free the list. What happens to buffer after it is allocated? Whenever buffer or block number 4 is allocated, then what happens? So the kernel may read data from the disk to the buffer and manipulate it, or write data to buffer and possibly to the disk. The kernel leaves the buffer marked busy. No other process can access it and change its contents while it is busy, thus preserving the integrity of data in the buffer. When the kernel finishes using the buffer, it releases the buffer according to algorithm B release, that is buffer release. This is the next algorithm for releasing that buffer. Similarly to the allocation algorithm, that is get block algorithm. Similarly, there is algorithm as B release for buffer release. See algorithm for buffer release. Here input is locked buffer, output is none. So when buffer is allocated, or that block is allocated for processing a data on that buffer, so that buffer marked as busy so that no other process can access it, change its contents while it is busy, thus preserving integrating of data in that buffer. So for waiting for that particular buffer, the processes went to a sleep mode. So wake up all processes that which are waiting for that particular buffer become free. Wake up all process events waiting for this buffer become to free, and raise processor execution leave to the block interrupts. If buffer contains valid but buffer is not filled old, if buffer contains valid and buffer not old, in queue buffer at the end of the free list. If buffer becomes free, buffer contains, that is buffer block number, then buffer number is valid and it is not old, then enqueue buffer at the end, that is store that or store that buffer at the end of the queue of the free list. If it is, if the condition, that is buffer contains valid and buffer not old, is not true, that is enqueue buffer at the beginning of free list, lower processor execution level to allow interrupts, unlock buffer. Okay, this is the algorithm for buffer release. Whenever, as per scenario, kernel assigns searches a particular block on its hash queue and that block is free, then kernel allocates, that is it frees from, it removes from the free list, and kernel allocates that buffer to particular process, and that buffer is marked as busy so that no other process can access it, change its contents, and whenever the work is completed, that block is releases to free, that is it becomes free by using the, or as per the algorithm of buffer release, that is B release. Whenever that particular buffer becomes free, so all sleeping processes wake up, and the processes which are waiting for particular that buffer also wake up. So if buffer contains a valid and buffer is not old, then enqueue the buffer at the free list. Otherwise, enqueue the buffer at the beginning of free list, unlock the buffer. Okay.